Happy Flex Day, everybody. It is time to keep on moving in the gas laws, Unit 11 packet. So we started with this packet that you see right here on this screen. We did that earlier this week. Now we're going to focus on the next part of this that deals with Boyles and Charles Law. Now, as you can see here, we're going to focus on the relationships between temperature, pressure, and volume by using different formulas that help us with this. If you look, turn in your page, so it's not basically the page we went over 2 days ago, not the 2 pages we went over yesterday, but on these 2 pages right here. So flip to where it says 11.2. We're going to focus on Boyle's Law and Charles Law. Essentially, we're going to talk about this. We're going to do this example, which is on the next page. We're going to talk about this, then we're going to do the example. So let's get into it. Let's take a look. First of all, we have Boyle's Law. Boyle's Law, named after, as you can guess it, somebody with the last name of Boyle. And what we look at when we do Boyle's Law is a relationship between pressure and volume. Gases have certain qualities that give us opportunities to measure things and to investigate the relationship between them. So we're going to look at what happens to the pressure when you change the volume and vice versa. So the first thing we're going to look at, if we have a little cylinder with a piston, this is a piston right here, and we are going to change that. We're going to move that. Now remember, the temperature is constant. We're not looking at temperature. We're only focusing on pressure and volume in this case. Temperature is not something we're looking at. So what if it says the volume increases? Well, what if then, if we took this right here and we move this up so that the volume inside increased, inside the cylinder. So this little red wall and the black weight on top is going to move up. If it does that, then molecules are going to hit the walls less often. If the molecules hit the walls less often, that means the pressure is going to be reduced. Again, what happens to the pressure if we adjust the volume? So in this case, we would say it's an inverse relationship, which means as one increases, the other one decreases, right? So as volume, in this case, we're going to increase the volume. So as we go along this way on the x-axis, what happens to the pressure decreases. So as one thing increases, the other thing decreases. The most important thing you want to get from this, though, is this equation right here. P1 multiplied by V1 equals P2 multiplied by V2. What exactly does the 2 and the 1 mean? Well, we'll talk about this in an example next, but it pretty much means initial and final. What happened first and what happened second? So let's take a look here. Here's a great example right here, Boyle's Law example. Now, a few things you should notice here are our units. On our units, we have ATMs here. Now, a few days ago, you learned there's torrs, ATMs, millimeters of mercury. There's a bunch of things. We can pretty much use whatever we want as long as the question, we know that the answer is supposed to be in that specific unit. So in this case, it doesn't say not to change the pressure from atmosphere ATM. So we'll just leave it at that. You also notice that we have it, the volumes in milliliters, which is fine too. We can actually leave those in milliliters. If the question said that make sure you change it to liters, that would be one thing, but there's no indication of that. Another thing you should notice, it does say constant temperature of 30, which means we really don't care about that because there is no T in this equation right here. So we don't care about the temperature in this case. Take a look. It says a sample of gas at 1.4 atmospheric increases. Okay, well, our atmospheres are a pressure, so that means in this case, we would actually call this a P1, right? It's a pressure, the initial pressure. It increases in volume. Okay, so here's a volume and here's a volume. Which one happened first? Well, it says from and 2. So from would be my first volume, and 2 would be 400 would be my second volume. And if you take a look right here, this says what's my final pressure, so it really wants to know what is my P2. I don't know my P2. So as you can see here on this equation, I have four molecules, excuse me, I have four variables. You are given 3, and you need to calculate 1. So I have this little table right here. I like this table. It helps out a lot. So I'm just going to put these in here to kind of organize my thoughts. And I already know my P1, my initial, is 1.4. My volume in the first situation, the initial situation, before something happens situation, is 250. The final here is, I don't know my pressure, so I put a question mark right there. And then right there on my V2, I'm going to go ahead and put 400. Now, this just becomes an algebra problem. I rewrite this just because I'm thinking about which formula I'm using. I substitute in, I plug in my numbers for each one of these. Each one of these has a number, and now all I need to do is solve for P2. And if I'm going too fast, just pause as you take your notes. Then I'm going to take this, the 400, I'm going to move it over to this side, and 400 divided in the denominator by the product here, 1.4, 250, multiply those, and that's going to give me a pressure. And by the way, those pressure units are still ATMs because that's what I started with. All right? Cool. Let's keep going. So we got Charles' law next. Charles' law is the relationship between volume and temperature. Okay, two new variables. Let's take a look at that. If we increase the temperature of the gas, so if we take this balloon and we move it inside, say it was outside, and now we're going to move it inside. If we move it inside, those molecules on the inside are going to heat up. The average kinetic energy of the molecules is going to speed up, and that is going to cause the balloon to expand. So as one thing increases, the other thing increases. And again, at a constant pressure, we're not worried about pressure. That means forget about pressure. There's no P in this relationship. So it's kind of like forget about pressure. It's at a constant pressure. You're here at sea level. No change there. So that means as one thing increases, the other thing increases. As temperature increases, this is called a direct relationship. The formula we're going to use for that is right here. V1 divided by T1 equals V2 divided by T2. All right? So that's the one we're going to look at here in this next equation. Now, my slide here had a mistake. Yours does not. Your paper does not. So I'm just going to fix that right off the bat. So here we go. We're looking for volumes, and we're looking for temperatures. Okay? A sample of neon gas is in a rigid 1 liter container at 15 degrees, has a pressure of 600 torrs. Now, we don't really care about pressure, by the way, because pressure is not in the equation, as you can see. What is the final volume? Okay, so I'm going to take some numbers here. What happened first? Well, what happened first was a volume of 1.0 liters. What temperature happened first? Well, 15 happened first. Now, here's something different. When we put temperature has to be in degrees Kelvin, or excuse me, Kelvin. There is no degrees. So that's something different. Temperature is different than volume, different than pressure. The units always have to be Kelvin. So that's easy. We'll use this equation right here. We're just going to add 273. So we take our 15, we plug it down there. 15 plus 273, and that gives us 288. What is the final volume? What? That's where we want to focus on. What's the question? The question is, what is the final volume? Okay, so let's put it in. What is the final volume? I don't know. Question mark. If the sample is heated from a temperature, remember it started at 15 and now it's going to go to 100. Now I can't put Celsius in there, so I just go 100 plus 273. I put that number right there. I am good to go. Now I can set this up using this. All I did was move some things around algebraically. I took this formula, made that formula, and now I can plug and chug 1 times 373 divided by 288. Of course, still want to use my sig figs, and 1.3 would be my answer in this case. 1.3 liters. What you're going to do next is you're going to go to the agenda, and you can see that these two things right here are what you want to focus on. So you'll click right there on Boyle's Law problems. You'll do those first, and then you do Charles' Law. Those will be what you would count for attendance. Take a look. Right here, here's the first question that came up for me. Of course, it's different for everybody, and it looks slightly different. So I'm doing Boyle's Law. I go and I double check what is Boyle's Law. And I say, I know what Boyle's Law is. Let me change colors. Yellow is sort of tough to see. So I know P1V1 equals P2V2. All right, so a sample of gas occupies a volume. So that's going to be my 350 right here, my 350 milliliters. That takes that right there. At 648 pressure, that's what happened first. So I'm going to go 648, kind of running out of room. So I'm just going to put a T right there. Equals what volume? I don't know. That's a question mark. So I'll just put a V2 right there. And it says 830 torr pressure. So I put that 830 right there. So all I need to do is solve for V2. So I divide both sides by 830. Both sides by 830, and then grab my calculator. My calculator that I dropped on the ground. That was fun. You don't have to do that for full credit. Don't worry. So I'm going to type into my calculator 648 times 350 equals, and then I'm going to divide by 830, and I get an answer, pretty crazy answer, of 273.2. 530, but it says 1 decimal, so I would type right in here, so I just type right in here 273.3 because 1 decimal. That's how I do that. Do that again.